Hello everyone. In this video of chapter Introduction to Polymer Chemistry, I'll be talking about classification of polymers on the basis of biodegradability and some polymers, their property and preparation. Classification of polymers on the basis of biodegradability. Most of the synthetic polymers are not affected by microbes. These are called non-biodegradable polymers. But there are some natural polymers like cellulose or you can say cotton. They used to be affected by the microbes present in the soil and turn them into the humus. That means they are biodegradable polymers. Non-biodegradable polymers, they remain in the form of waste material and stays in environment for very long time, and they will become pollution hazards. In attempt to tackle the environmental problem, scientists have developed biodegradable synthetic polymers, and they are quite successful also to develop such polymers which are biodegradable. We will learn some example for biodegradable, but right now we are going to learn some polymers, and one of the polymer is rubber. Rubber is the elastomer. Commonly we used to call this such elastomer is rubber. For example, rubber is used to make balloons, shoe soles, tires, surgeons' gloves, etc. They all are elastomeric material, and you can say they are made up from rubber. If I talk about natural rubber, natural rubber monomer is 2-methyl-1,3-butadiene, and this is the structure of the compound. Natural rubber is a higher molecular mass and it is a linear polymer of isoprene. This compound is also called isoprene, and the molecular mass of rubber would remain from 1,30,000 to 3,40,000. This is the structure of natural rubber. And if I want to talk about its reaction, how it is forming, this is the reaction involved where n number of molecules of isoprene is taken and it will be polymerizing to give you polyisoprene or rubber. Here what had happened, this and this bond is broken down, these two valencies are free of these two carbon atoms, and on rearrangement these two carbon atoms are developing double bond in between them. The structure is called as rubber. Now again, let's talk about the properties of natural rubber. Polyisoprene or natural rubber molecule has a cis configuration of carbon to carbon double bond. It consists of various chains held together by weak van der Waals force, and it is having a coiled structure. It can be stretched like a spring and exhibits elastic property. Now, vulcanization of rubber. To improve the physical properties of natural rubber, the process of vulcanization used to be carried out. In 1839, Charles Goodyear, an American inventor, invented the process of vulcanization, and in this process what happened, there is a network of cross links is introduced into the elastomers, and the process would be called as vulcanization. Sulfur is the element which is frequently used for this process, and sulfur forms cross links between the polyisomers chain which result in the improvement of the properties of natural rubber. Like you are seeing, this is one strand of polyisoprene and this is another strand of polyisoprene, and sulfur is linking these many strands by such kind of bond. It is carried out by heating of raw rubber with sulfur powder in presence of some organic compound called accelerators at about 423 Kelvin. One or more sulfur atom cross-link to polyisoprene chain, and cross-linking take place by opening of double bond and produce 3D rubber molecule. Vulcanization is a process by which we used to strengthen, or you can say that increase the tensile strength of a rubber. Now another polymer, polyethene. Polyethene is a simple molecule, or you can say it is the simplest and most commonly hydrocarbon thermoplastic. Ethene is the molecule having carbon to carbon double bond, and each carbon is bonding with two hydrogen atom, and this is the polythene molecule, and you can say this is the repeating unit. The IUPAC name of polyethylene is polythene. Polythene is also of two kinds, LDP and HDP. Now LDP and HDP. LDP means low density polythene and HDP means high density polythene. It is low density polythene is obtained by polymerization of ethene in the presence of traces of oxygen and peroxide at 350 to 370 Kelvin, and the pressure used to remain 1000 to 2000 atmosphere. When in such condition ethene is polymerizing, it will give you low density polymer. It is a branch polymer. LDP films are extremely flexible but tough, chemically inert, and they are moisture resistant also. It is a poor conductor of electricity and it has melting point 383 Kelvin. Preparation of pipes for agriculture, irrigation, submarine cable, insulation, squeeze bottles, attractive containers, insulation to electric cables. These all are the uses of LDP or low density polythene. If I talk about high density polythene, if for preparing high density polythene or HDP, I need to take ethene molecule and I need to subject this molecule or at temperature 333 Kelvin to 343 Kelvin at the pressure 6 to 7 atmospheric with catalyst. Here catalyst involved is called as Ziegler-Natta catalyst. It is also a linear molecule and it is crystalline. Its melting point, it's in between the range of 417 to 423 Kelvin. It is stiffer than LDP and it has high tensile strength and it is quite hard also. It is more resistant to chemicals than LDP. Manufacturing of toys, other household articles like buckets, dustbin, bottles, pipes, these are the things which used to be prepared by HDP, or you can say high density polythene. Now Teflon. Chemically, Teflon is polytetrafluoroethylene. The monomer used for tetrafluoroethylene monomer used is tetrafluoroethylene, which is CF2 double bond CF2. Tetrafluoroethylene is polymerized by using free radical initiators such as hydrogen peroxide or ammonium persulfate at high pressure, and tetrafluoroethene will polymerize to give you Teflon. Properties of Teflon: it is tough, chemically inert and resistant to heat, and it is it remains resistant to the corrosive reagents also. CF bond is very difficult to break and remain unaffected by corrosive alkali. That is why it will not corrode that easily. Uses: Teflon is used in making non-stick cookwares like cooking pan, and it is also used as oil seals and gaskets, etc. Another polymer is polyacrylonitrile or PAN. Polyacrylonitrile is prepared by addition polymerization of acrylonitrile by using peroxide initiator. We need to take acrylonitrile in presence of peroxide. It will give us polyacrylonitrile. Polyacrylonitrile resembles wool and it is used as a wool substitute for making Orlon or acrylan. Orlon is used to make blankets, shawls, sweatshirts and sweaters. Now polyamide polymers. Polyamide polymers are generally known as nylons. Nylon is a generic name of the synthetic linear polyamide obtained by the condensation polymerization between the dicarboxylic acids and diamines. The self-condensation of amino acid or by the ring opening polymerization of lactams. Polyamides generally contain a linkage of CO single bond NH, or you can say secondary amide groups. And the two important polyamide polymers are nylon 6,6 and nylon 6, which we are going to study. Now Preparation of nylon 6,6. The monomers adipic acid and hexamethylene diamine. This is adipic acid and this is hexamethylene diamine. On mixing form nylon salt, which upon condensation, the polymerization reaction happen at high temperature and pressure, which will give you the molecule nylon 6,6. Nylon 6,6 is used for making sheet, bristles for brush and textile industry. The numerals 6,6 in the name of this polymer stand for the number of carbon atoms in the two bifunctional monomers, namely adipic acid and hexamethylene diamine. Nylon 6 has high molecular mass from 12,000 to 50,000 unit. It is a linear condensation polymer. It possesses high tensile strength and it does not soak water. Another polymer is nylon 6. Nylon 6 is obtained from epsilon caprolactam, and when it is heated with water at high temperature, it undergoes a ring opening polymerization to give you polyamide polymer, which is called as nylon 6. Here, this is the molecule of caprolactam, and when the ring is broken down and it is becoming the open chain compound like this, the bond between NH and CO would be broken down from here and it will give us nylon 6. Then the polymer is obtained is called nylon 6. The nylon 6 is given on the basis of 6 carbon atom present in the monomer unit. Due to high tensile strength, the luster nylon 6 fiber are used for manufacture of tire cords, fabric and ropes. Now preparation of polyesters. The polyester polymers have ester linkage joining the repeating units. Commercially, the important polyester fiber is terylene and it is also called Dacron. Dacron or terylene is the best known example for polyester. It is manufactured by heating the mixture of ethylene glycol and terephthalic acid at 420 to 460 Kelvin in the presence of zinc acetate antimony trioxide catalyst as per the reaction. Now, let's see the reaction of the preparation of Dacron. Here, ethylene glycol we have taken and terephthalic acid we have taken. This is the reaction where the esterification is going to happen at this temperature. Water molecule will be eliminated and to give you terylene and Dacron molecule.